I'd like to thank organizers, especially for their patience, because I was not responsive, but still giving me this opportunity to talk. And I also have to apologize for the audience who are experts, because what I talk, most of the thing is like prehistory in renormalizations. But since this is the first talk, I wasn't sure how much of the audience are familiar with renormalization. So let me start with the basic. And uh, so I'm sorry for those people who are bored with this talk. Okay, so what is renormalization? Do you see the top part of the window? So the renormalization is a way to define a new dynamic systems from a given one via the first return map or some sort of first return map to a subset and rescaling. So probably instead of speaking about abstract setting, let me start with a well-known example, which is not exactly complex dynamics, but it's about real dynamics on the interval, the unimodal map, and it's called the Feigenbaum-Klesse renormalization. So start with a map, the real map on the interval like this, and suppose that the shape of the graph looks like one hand, and then second iterate. It's not always, but sometimes it has a shape like this. And under certain condition, you may find a sub-interval here, such that the second iterate comes back to itself as a 2-to-1 mapping. So in this case, for the second iterate, you draw this the box, and its image will be here. So first map of f sends this interval to that interval, and the second iterator will come back. So in this case, just to restrict the map to the smaller interval and rescale the interval. In this case, it's the opposite direction for the unimodal map. So you may switch the orientation, and you get the new map from the restriction, which looks again the unimodal map like the original map. So the new map, so coming from the restriction of the second iterate, and then conjugated by the scaling map G, is called renormalization of F, defined on this subinterval J. So in a sense, this is a certain kind of operation or map. For given F, you get a new dynamics RF. So later, we consider that this operation is a map in a certain space. But anyway, well, you don't always have this invariant interval, but just in the case, if you have such an interval, you are able to define from F, the R of F. This is called renormalization. Okay. So this is the idea of renormalization for the unimodal map. So essentially taking this sub-interval, and you iterate until the orbit comes back. In this case, you need a second iterate to come back and restrict the map here. And to make the interval unit, you have to rescale or flip the orientation. So this process is called renormalization itself. So by renormalization, I might mean the renormalized map RF itself, but also the operation itself is called renormalization. Okay. So in general, this is a kind of abstract schematic picture. Renormalization in general, that you have a dynamical system, a map defined on some space, and take a subset in the phase space, and then suppose that there are a certain number of orbits will come back if you start from here. Then you take this subset and rescale it to some unit size. Or in abstract setting, you don't really have to rescale, but later on, this rescaling map may mean something different than just scaling a finding. And then forget about the intermediate orbit, and for initial point, you correspond this final point of the return, and that will define a partial dynamics starting from here, the return point here, and that is a renormalization in general. So from F, you construct in general, RF is not the entire dynamical system on the whole subspace. You may have to restrict to some subset, but this is a kind of important idea to deal with the dynamics. So here, one construction is not a very deep thing, but I'd like to discuss about infinitely renormalizable maps. So by this, I mean that you can do this construction infinitely many times. So that means here you have a dynamics to start with and take a subset, good subset, so that some return map is defined. Then after rescaling, if it's necessary, you get the new phase space and dynamics or partial dynamics, and you take this certain subset again, and then from this you construct a return map and so on. So from F, you construct the R of F, then R second of F, and third of F, and so on. I'm interested in the case where you can define this for a suitable choice of this return subset infinitely many times. So when this can be done infinitely many times, the map is called infinitely renormalizable. Of course, this construction depends on the choice of this subset. And each time you may have a different subset, but for the moment, I don't discuss too much about this choice. But when you have this construction, I say that it's infinitely renormalizable map. So it doesn't always happen that the map is infinitely normalizable. So when we assume that the map is infinitely normalizable, it's already some special case. But there are a lot of interesting phenomenon, and there is also important meaning for infinitely renormalizable maps. So the goal is that you want to understand the original map, but still you construct this sequence of renormalization. And what you want to do is, given this sequence of renormalization, you recover some information about original map, or maybe a family of the maps that contains this F, or another map with the same type of infinite renormalization and so on. Okay, so this is the goal of this talk. And what kind of map has this infinite renormalization property, I will discuss later. But so if remember that when you restrict, say, a small subset, it may take some time to come back. So it's possible that some high iterate of the original map correspond to only one iterate for the return map or the renormalization. So that means next time, next level for the renormalization you're doing again, so you may have several iterates to come back. That means it takes even larger number of iterates for the original one. So essentially, by doing this, this small number of iterates for the renormalized map respond to high iterate of the original map. So you can analyze this high iterate. So in general, when you perturb the map, the high iterate depends very sensitively on the initial map. But if you assume that there's an infinite renormalization, there's a way to control a high H rate of the original map. At the same time, so this is applying this rescaling and so on. So small set is somehow blow up, like the previous in slides. Small interval is blown up to the unit interval and so on. So small subset is blown up to somehow unit size or canonical size. And then in this set, you get another small set, which is blown up to the larger scale and so on. So if you take, for example, here, some certain finite level of the size, then that corresponds to the small structure in the original map. So this allows us to analyze this fine orbit structure for the dynamics, the initial dynamics F. So this is a kind of idea that you can use the renormalizations or sequence of renormalization to analyze the original map. So why do you want to study the renormalization? Okay. The first motivation came from this physics. So before the dynamics in mathematics, there were the theory of renormalization in statistical physics. And there were a lot of studies about the critical phenomena. So critical phenomena is more or less like our infinite renormalizable case. And some universal scaling phenomenon was already observed. And that observation was transferred to the dynamical systems. And the first case it was applied was the sequence of period doubling bifurcations, which I mentioned in the next slide. So it's due to Feigenbaum and Coué-Tressé. Okay, and there are other reasons to study the renormalizations. So it's a rigidity problem. So rigidity, in a sense, in this setting, it is like an automatic upgrade of conjugacy. So suppose you have two dynamics and somehow you have a topological conjugacy or even weaker combinatorial equivalence. And it sometimes implies, surprisingly, that automatically implies the higher regularity of the conjugacy. So only assuming the weak one, you get the stronger one. So this is automatic upgrade. So the higher regularity means sometimes QC or smooth or several different category, which is much better at least than topological conjugacy. Okay. And the rigidity phenomenon is not only in dynamics, but in a general motivation in mathematics. So there are various cases the rigidity phenomenon was discussed. In complex dynamics, this rigidity question was very important above all. Because it is closely connected to the density of hyperbolicity of rational maps or polynomials. And the hyperbolicity I'll discuss later, but hyperbolic maps are the class of the maps which are well understood and easier to handle. And the density means that there are plenty of those understandable maps. And in this, the largest generality, this is still an open question, but this line of question was considered in some special cases, especially for the quadratic polynomials. Sullivan started to think about these questions, applied some argument about that the rigidity somehow implies the density of hyperbolicity, and the result, the positive result of density of hyperbolicity among real quadratic polynomials was obtained by Lubitsch and Gracek-Swiatek. Okay, so this is related to this the MLC conjecture, the local connectivity of the Mandelbrot set. There are also the density of the rigidity question was a key to attack those questions. And for the MLC conjectures, there was a work by Yokos. He has dealt with the cases where the maps are not renormalizable or not infinitely renormalizable, and he showed basically the rigidity result or the local connectivity of the Mandelbrot set. And the Lubitsch or Count Lubitsch and other people have worked out the large case of the local connectivity result in a complex. But I think for general cases, it is still open. I might be ignorant, but as long as I know, this was the open question in general case. For non-quadratic higher degree polynomials, for real polynomials, there was a big progress that the hyperbolic real polynomials are dense, and it was due to Kozlowski, Shen, and Landstrian. And this was also attacked via the rigidity questions. So that means suppose in certain sense, two maps or say two real polynomials are combinatorially equivalent, and then ask a question whether they can be, say, QC conjugate. And by solving these questions, they obtained a positive answer for the density of hyperbolicity. The last line, so this maybe I should have mentioned earlier, but there's a Sullivan's dictionary, which was mentioned by Hubbard Stock. So dictionary between this complex dynamics and action of Kleinian groups on the sphere, two sphere. And so the rigidity question on the other side of the dictionary, this it corresponds to the most of rigidity about the Kleinian groups. And so besides these, the reasons, renormalization itself is somehow mysterious thing because, well, I'm going to define it, but it defines some kind of infinite, starting from a complex one-dimensional dynamics or real one-dimensional dynamic. So suddenly you go to the infinite dimensional space of the dynamical systems and define the dynamics there. And it's amazing that you can say something about those objects. So as I mentioned, renormalization operation constructing from F, the R of F can be thought as a self-map of the space of dynamical system, some class of dynamical system. For example, in the first example, I mentioned that for the Immortal maps, excuse me, space of Immortal maps, and then you create a new Immortal maps, which are defined on the subset of this space. So it's a self-map or partial self-map of this infinite dimensional space. So in a sense, this can be considered as a meta-dynamic. So initially, it's only a one-dimensional dynamics, but somehow you get the infinite dimensional space of the dynamical systems, and you got the self-map by using this first return maps. So for the first glance, it looks hopeless to study such a things, but suddenly you're getting infinite dimensional object. But somehow it's amazing that you find often the nice structure for those maps, especially, for example, for this Feigenbaum-Couret-Plessé renormalization, there's a fixed point. And it's not only a fixed point, but it is a hyperbolic fixed point. And unstable direction is one-dimensional, and stable direction is codimension one. and then I'll tell you how to use this fact to conclude some result about bifurcation and so on. More general cases, it's not only fixed point, but you find some invariant set on which the renormalization in more general sense is acting, and you obtain some horseshoe-like structure and still hyperbolic, and this has a conclusion about rigidity or bifurcation and so on. So let me go with the most classical case for this unimodal map. The most studied family is, one of the most studied families like AX times 1 minus X, the logistic family, or it's equivalent to X squared plus C. And the picture shown is a bifurcation diagram. So this horizontal axis is the parameter A, and the vertical axis is like orbit of iterates, and after first iterates are neglected. So for small parameters, you have attracting fixed point, then it bifurcates the period doubling bifurcation into period 2 attracting cycles, and that bifurcates the period 4 cycles, period 8, and so on. So you can define the bifurcating parameters A1, A2, and so on. And then it converges to a certain limit, A infinity. Okay. So it was observed first, well, conjectured and observed that there's a kind of limit that, so there's a infinity somewhere here, and compare the distance between these two and these two, and this ratio between the limit and n and limit and the n plus 1 has some limit. Not only there's a limit, but if you take the different families, which looks like a unimodal map, this limit is the same. So it's not only there's a limit, but this limit is universal for the unimodal families. And that was quite an amazing phenomenon. And the explanation using the idea from this statistical physics was following. So I told you that for this period doubling case, you can define from an original map, when you have this invariant interval, you get the second iterate and restriction, and rescaling, get a new unimodal map. So this is a map from F to R sub F. Then you suppose you can iterate this. And then, as I mentioned, this is a metadynamic in the infinite dimensional space of unimodal maps. And the claim was that there's a hyperbolic fixed point with one expanding eigenvalue and the codimension one contracting directions. So the picture is like I showed you before. So this is a whole space of the infinite dimensional space of unimodal maps, and there's a subset where you can define this renormalization. And then the claim was that there is a fixed point on the F. That means our capital F is equal to F. And then there's an expanding direction and a contracting direction. So if you take arbitrary family and generic family in this space, so it is expected that you cut across this space the stable manifold of codimension 1, and this intersection with one parameter family with a stable manifold exactly correspond to the infinity, and there's a codimension 1 submanifold where the period doubling occurs. Actually, period doubling occurs when you have a fixed point with a derivative -1, so it's easy to characterize. So it's a codimension 1 submanifold. But if you renormalize, there's the inverse of this submanifold, which is mapped to this green one. by R. Then here, that means after you take a second iterate, it has a period doubling the bifurcation. So that means for the map itself, it is a period 4 bifurcation. So that corresponds to here. So intersection here would correspond to A1, but the next intersection with this one would correspond to A2. And then similarly, take an inverse image, the intersection will correspond to A3. So that means just suppose you look this picture from the direction of a stable manifold. There's a stable manifold fixed point, and then these invariant manifold or period doubling, and period doubling for 2 to 4 and 4 to 8, and you have one parameter family and corresponds to here. So this ratio is measuring the distance between this AN to A infinity and AN plus 1 to A infinity. But when you have these hyperbolic structures, this ratio should be proportional to this expanding eigenvalue delta, which is greater than 1. So this should be expanding eigenvalue. So if you just look at one family, it is kind of amazing fact that there's even a limit. But if you put the whole picture into the space of the dynamical system and consider the renormalization map, it is very natural that you have this this ratio converging to some limit, and the limit is the same for other families, for generic families, because if you take a different families, you still have the same limit. And this explains the universality of this bifurcation ratio of this form. Okay, so this was the initial starting point of this Feigenbaum Cretresses theory. And the first claim like this was given by Oscar Lanford using the computer-assisted proof. Existence of this fixed point was given by Henri Epstein using complex analytic techniques. But later on, there was work toward this claim, or more generalized claim, using more theoretical or conceptual approach, started by Dennis Sullivan, and in a general case, given by Michel Lubitsch. But well, that was a starting point for this normalization theory. So I mentioned the rigidity between between the same type of map via the renormalizations. So what is this? Still, I think well, it's complex dynamic conference, but it's easier to explain with the unimodal map pictures. So let me go on with the unimodal and period doubling renormalizations. So when you have infinitely renormalizable map, I said that I'm interested in infinitely renormalizable map, and in this case, I always assume that it's renormalizable by period doubling constructions. Then there was a first interval and its image to start with, but after first renormalization, well, you have to rescale it, but for the moment, forget about the rescaling, get the invariant intervals for the renormalized one, and then there are its image by the original dynamics, and then you can continue for forever by these constructions. So each time you get the two intervals inside the previous level of intervals. So each time you get this proper subinterval from the original one, and eventually, and you can show that these sizes of intervals shrink, and as an intersection, you get a Cantor set, invariant Cantor set for this infinitely renormalizable map. So now suppose you have two such maps, and they have the same combinatorial type. Well, it's not necessary here that you have a period 2, but it is necessary to require that you have the same type. So for example, here, using only a period 2 here, but you can assume that period have 2 for the first level, and next level you have the period 3 and period 4 and the period 2 again, and so on. Say, for example, let me assume that this is a bounded period of renormalization. Then the rigidity, I said that it is like automatic upgrade of the conjugacy. So for this type, the combinatorial type is like this commutation. This no, the periodic combinatorics of these intervals, and so under this assumption, they have a combinatorial equivalence. But the conclusion that is stronger. So here I have to assume that say F and G are C3, or you can weaken this assumption, and the critical point is non-degenerate. Then there exists a conjugacy such that connects these two maps P, that it is a conjugacy, and it is say on the counter set. Sorry, I forgot to write. There's a limit counter set. Okay? So it's not just a topological conjugacy, but on the counter set or the restriction to counter set is like a smooth 1 plus Helder regularity. So this is, like I said, the automatic upgrade of the conjugacy. This follows from the fact that the sequence of renormalization. So here I'm assuming that both are renormalizable with the same type. And so assuming that these two are in this the same class, this implies that the F and G are the, for example, in the period doubling case, the stable manifold of the fixed point. And so when you have a hyperbolic structure, and this is a codimension 1 stable manifold, the distance in certain good metric will go to 0 is exponentially fast. And so if you know this fact, from that you are able to conclude this type of the regularity result. That means the rigidity result. So if you know this exponential convergence, that means first renormalization is about here. So you're comparing the phase space of two maps here, and second renormalization is comparing here and here. So, and then the structure in the image will be connected by this the dynamics itself. So if the structure are similar here, the structure in the image is also similar here. So that means if you have a result of this type, if you kind of zoom into this the fine structure of the Cantor set, the fine structure is exponentially similar. Okay. Of course, initial stage the F and G are not very close, but somehow bounded distance away. And next stage, well, they are not exactly the same, but getting closer and so on. Since this size is shrinking exponentially small, and the fact that this fine structure is getting similar exponentially, you combine these results to obtain this the C1 plus alpha conjugacy. So to go back to this original map, starting from, say, nth level of renormalization, to go back to the original one, you have to use the combinatorics to know that you have two maps. So if they are similar here, use these dynamics to go back to this larger scale using the combinatorics here. So there's a combinatorics hidden here to conclude the rigidity result. Okay. For circle maps, there are also an idea of renormalization. Here, you take the circle or the unit interval, and if you have a critical point, you mark this point, or otherwise you mark one point arbitrarily, and partition the interval by its orbit or inverse orbit. And so repeating this subdivision by the inverse orbit, for example, of this point, you get the final partition of the interval. And in this case, the common formulation is, instead of circle map itself, people have used the so-called commuting pair. So you consider the map in a larger class where you have a one map F1 and second map here, two branches, and assume that they are defined near this cutting point. And on the cutting point, these two iterates are defined, and assume that they coincide. So this is a pair, the commuting pair, and the renormalization was defined in this space of the commuting pairs, such that this renormalization is from F1 to F2. Either you just take composition here and F2 itself, or in general case, F2 and F1 some iterate and F2. And this again gives you a commuting pair, and possibly you have to rescale the interval because this pair is defined on the subintervals. So here, before the Feigenbaum case, it was like the odometer mapping, so like two partitions. But here, the partition of the subintervals are closely connected to the rotation number, or the continuum fraction expansion of the rotation number. Okay. Oops. And there are a lot of work done in this direction, and with especially with the circle map with one critical point like this. And even in this case, if you have a convergence of the renormalization in a certain sense, you obtain the rigidity result, so that two such maps with the same rotation number, same combinatorics, conjugated by the smooth map. These are two examples, just to have some idea about renormalization. But let me discuss a little bit about the two extremes in dynamics. So there is one kind which is very tame and zero entropy minimal dynamics. One is the chaotic dynamics or expanding dynamics. So one is very fragile, easy to destroy by the perturbation. The other one is robust, stable, or structurally stable under perturbation. And one is rigid in the previous sense. Somehow within the same class, the conjugates automatically smooth. And the chaotic part, the conjugacy is not smooth. So in a sense, the tame class, it's a dynamics itself is very tame, but very delicate to deal with. On the other hand, the chaotic one, dynamics itself is chaotic, but it's easy to study by the expansion or hyperbolicity of the dynamics using the Markov partition or other method. Okay. The typical example is a irrational rotation on one side and the doubling map on the other side. So this one is chaotic, this one is very tame. And the other example is like for the hyperbolic surface, the unit tangent boundary on the hyperbolic surface, there are two objects or even three. One is geodesic flow, which is chaotic. The other one is holocyclic flow. They're actually stable and unstable holocyclic flows. And somehow they are in the two extremes in dynamical systems. But often these two extremes are connected each other. For example, this circle map, if you try to conjugate or semi-conjugate the irrational rotation by the chaotic doubling map, the result is like a second iterative of the original irrational rotation for geodesic flow on the tangent boundary of the surface. Again, you have this relation. So this was the flow, and on this side you have the HT holocyclic and the time change of the holocyclic flow on one side. And for symbolic dynamics, you have a well-known shift map, which just to forget about the first one and shift. And on the other side, there's adding machine dynamics, which is like automata dynamics. So when you have adding and carry to the right, you have this dynamics. In this case, again, you have a relation between this. So tau is this one, this tame one, and try to conjugate or partially conjugate by this chaotic one to get the second iterate. Actually, it is very similar to this one. And if you know this, that for Feigenbaum limit Cantor set, the dynamics is conjugate to this adding machine, and rescaling correspond to this shift map. So, for example, for Anosov differ on two torus, you can associate irrational flow, and when you have irrational flow, you can combine. Well, this is a case where you have, for example, golden mean rotation or the quadratic irrational numbers. But in general, you may have to change these f's so that you have certain relation. So in a sense, the conjugation by or semi-conjugation by chaotic one is like a time change for the tame map. So going back to the renormalization is exactly the connecting the these two extremes in dynamics. So for renormalizations, the target is, I said, the infinite renormals of a map. And these are very tame and delicate maps, like a Feigenbaum map, so irrational rotation. But suppose given such a map, you construct a sequence of renormalizations. So this is, in a sense, in this case, this is expanding map. And it is not a dynamics in the sense that it's not a map from one space to the same space, but it's a mapping from one space to another space. And this one from this space or a subset to the another space and so on. And this is like a fixed point of the renormalization. So this is you get the different spaces for each one, but somehow this has an expanding nature, and the chaotic dynamic argument for chaotic dynamics can be carried over to this expanding composition of the maps. Okay. So in a sense, the expanding nature of a connecting map of these target maps helps us to study the target map, because this single map itself is very fragile and difficult to study. But with the help of these expanding maps, or the renormalization, which is a meta dynamic, we are able to conclude something about the dynamics. So another feature here that we saw this Cantor set. Essentially, the renormalization is sending this to a unit scale, or this one to this unit scale. So this part is this expanding map. So for renormalization, if you can conclude this something, you can conclude about the fine structures of this initial map, and this was a way to construct the smooth or C1 plus alpha conjugacy along the Cantor set. Okay. So there's also another reason to study the renormalization and rigidity. Well, I think there are a lot of content along this direction, but let me go very quickly. So there was results by Manisov, Sullivan, and Lubitsch that in a family, complex analytic family of rational maps, the trajectory stable parameters or J-stable parameters are dense. And on the other hand, I mentioned that density of hyperbolicity is one of the open questions in general setting. So the conjecture says that in the space of rational maps of degree D greater than 1 or polynomials, hyperbolic maps are dense. Well, the Duadi-Hubbard theorem says that for complex polynomials, if you know the density of hyperbolicity, you can conclude for quadratic polynomials, the Mandelbrot set is locally connected. And that helps to understand the whole picture about quadratic polynomials and parameter space. On the other hand, Yoko's work allows us to study the I see, it's not infinitely normalizable. Sorry, it's missing. Then the Mandelbrot set is locally connected. So the remaining case is infinitely normalizable case. So along this direction, there is of interest that we want to know the rigidity of this infinitely renormalizable maps. So this is another reason to study this rigidity and renormalization. And for real ones, I mentioned this result already, and the proof was given through the rigidity. And the general framework for full renormalization conjecture for real maps, including many cases for the complex renormalizations, was done by Lubitsch and his collaborators. But let me, keeps this one solid. So there are various kind of renormalization.
Sorry, Mitsu. Just maybe a quick comment for anyone who sees it the first time. I think on the previous slide, when you mentioned the theorem of Duadi and Hubbard, I think it's the other way around, right? So if the Mandelbrot set is locally connected, then hyperbolicity is dense.
Oh, sorry. I haven't done this for long years, and it was opposite. Sorry about this. So I mentioned two types, and it was easy to go back to this original map if you know this sequence of renormalizations. And I plan to discuss about this sector type renormalizations where these natural partitions of the phase space doesn't exist. This was the case where you have a map of this type, say complex mapping with the fixed point with derivatives like irrational rotation. Then you can't really divide. This dynamics doesn't really give you the natural partition of the phase space. So I have to wrap up this talk quickly. And in this setting, there was a work by Yokos for the Ziegler-Bruno theorem about the linearization, which is the construction like this. So starting with this fixed point of this type and take the straight line starting from the fixed point and look at its image and take a smaller subset so that it is nice. And then you can glue together with the first segment as image by the dynamics, get the quotient space, which is known to be the puncture disk if you normalize. And then again, for this sector region, you can define the first return map to define the new map. So this defines the sequence of renormalization. And we know that once you know alpha n, what should be the alpha n plus 1, which is like a inverse modulus the integers. And you may have to cut off a certain part of the dynamics to be able to define the renormalization. And if you want to go back to this original map, again, you have to add in some dynamics. So it's not always possible to understand this original map, even if you know something about the sequence of renormalizations. So here comes the idea about so basically space segment is here and the image is here. So to glue, to have some nice manifold structures, you have to take a neighborhood of this initial segment and its image. So that means you just cover those fundamental sector, and the fundamental sector may look like this if you, in a sense, uniformize, and then gluing this overlap region to obtain this renormalization. This is the picture in this irrationally indifferent fixed type. And then you again do the same for the renormalization. So to go back to the original dynamics, it is always a problem that you have to glue. It's not a partition to start with. And this cutting was not canonical, and it was arbitrary, and there were ambiguity to start with. But anyway, this construction forward was used by Yokos to study the Ziegler theorem or Bruno theorem, and backward construction was used also for the converse of Ziegler-Bruno theorem. So here I wanted to introduce the idea of the dynamical chart in the sense that you just take a canonical space for this one, so that you have an overlap. You allow the overlap. So like the definition of the manifold, you define this some canonical space here, and then the gluing of the boundary regions to the next one. So you have 5 canonical domains, then you glue them together to obtain punctured neighborhood. And then there's a canonical dynamics between this canonical coordinate. This is somehow some canonical maps. And glue them together, you recover the original map. And then if you know, this corresponds to the first renormalization because you are taking this one first sector of the fundamental sector straight segment is image, which is uniformized like a half strip of this shape, like this shape. And but the next renormalization is starting from here. After renormalize, don't go to this picture, but stay with this picture. And then there's a new renormalization will be giving a subset, again, which is like a strip, half strip, and then glue them together, obtain some, this one corresponding to this, these smaller sectors in the original dynamics. But to recover the original max with all small sectors, you glue these smaller sectors, or the half strips, and the dynamics on these half strips, and so on. So this can be carried out. This idea can be carried out for. So I think I wanted to mention about the formulation, but if you know the definition of the manifold, it is a natural thing to define. And there's extra thing about the index set, how to glue them together. Well, when you have a manifold, you also have a combinatorics of how to glue these charts and to recover the original dynamics. And this idea can be used to understand the irrational dynamics for a certain class of dynamics. So this, let me just say, there's well, not the whole all the classes, but for some subclass, which I don't define today, but for the irrational rotation number with very large entries in continuous fractions, you are able to carry out someone, including this quadratic polynomial, and conclude about the local dynamics. Here, I assume that when you have this irrational continuous fraction expansion, you have large ones. So let me just to say, a typical conclusion you can derive is that the rigidity type result, when you have two maps in the same class with the same combinatorial type, which is rotation number, I assume a high type, then they're conjugated by QC maps in an invariant set, but slightly better than the QC that is asymptotically conformal at the critical point. So I wanted to say that I apply this idea about the dynamical chart, but this is the only case which was applied, that I'm hoping that there are more applications about different renormalization, different settings when you can't have a natural partition, but you have to have some overlap to construct a sequence of renormalizations. And this is it. I'm sorry that I had to go quickly at the end. And I'm also sorry for the people who have heard these some prehistorical part of the talk. Okay, thank you very much.
Thank you. Do you have questions? No questions. Oh, there is
Mitsu,
one question.
maybe. So I think there was a point that you were making at the end about the domains of the renormalization. So you were saying with the if you kind of start with the sector renormalization, you don't really have a canonical choice of your domains. And so I think you were saying that with the kind of further refinements of this, you do have some canonical way of choosing your domains, and that's what allows you to get stronger conclusions about the dynamics. Can you maybe say that again a little bit more slowly? That would be great.
Yeah, so it is about the Yoko's renormalization. So there was this construction that you start with a straight line and its image, and take some region bounded by this straight line and its image, and some kind of arbitrary segment. And if the rotation number is very small, you are forced to cut this in a very deep, so that you're able to define this gluing and have some control about this gluing and uniformization of the punctual disk. So somehow there's a missing part here. And for the Ziegler-Bruno theorem, it was okay that if you assume that the rotation number is Ziegler-Bruno, this cutting of this doesn't occur too deep, so that it doesn't grow too fast. And you still have some region remaining, so that it corresponds to this linearization domain for the germ of this type. Okay, so the next question was that so when you have like a Kramer type example, so you don't hope that you have a linearization, but still you hope that you can say something not just at a fixed point, but with something including some larger domain, especially when you start with the quadratic polynomial, you have a critical point. And it is known that the critical orbit is very important for this Kramer type dynamics. So you want to include the critical point for this type of renormalization. So for that definitions, the Yoko's renormalization is cutting too far. That's why we needed to introduce another type of renormalization. So that was the reason that we introduced the near parabolic renormalization. But you have to assume, unfortunately, that the rotation number is very close to the parabolic. That means for rotation numbers, this continued factoring, the coefficients are all larger than some big number n. So that means you have a fixed point and another fixed point, and they are very close to each other because they are close to the parabolic point. But in this case, we are able to determine one class of the map so that it is closed under the renormalization. If you and you are able to deal with the critical point. So this is the difference between these the domain of definition for renormalizations. Anyway, thank you for asking these questions because I wasn't really explaining.
Thank you.
Okay.
Some more questions?
Yes, so I'd like to ask about this relation between chaotic dynamics and tame dynamics. So in the case of almost parabolic renormalization, what's the chaotic dynamics associated?
So chaotic dynamics, well, the limit case is very easy to define. So instead of the irrational numbers, you just take a virtual. Well, I mean the virtual world now. So take a rotation number like 1 over infinity plus 1 over infinity and so on. In that case, two fixed point collapse. And this is like a Fatou coordinate going to here with quotient by z. And then you are taking exponential. So the Fatou coordinate is not a very drastic thing. Once you change the coordinate so that fixed point is at infinity, the biggest thing you do is taking the exponential map, because here you have by infinite cylinder C over Z. To introduce the next generation renormalizations, you have to take a punctual disk. So this chaotic part of the dynamics, or the gluing or connecting map, is exponential map together with very mild Fatou coordinate. So essential part is given by the exponential map. And after bifurcation, you have to modify this by something else. But typically, it is very close to the exponential map in a certain sense. So somehow there's a hidden dynamics, which is not dynamic itself, but it's a sequence of composition of exponential-like maps. That's why you see the hedgehog-like structure or Cantor bouquet. Okay. That's
I also have a question. Maybe it's a simple
structure.
one, but is there a natural way how to embed this real unicritical renormalization into the framework of renormalization of quadratic polynomials in complex? For complex polynomials?
The real renormalizations these days, it is studied via complexification of the dynamic. So one they can study this, the result about renormalizations. For example, Ljubich's work about the full renormalization conjecture. He actually studies the complexification and so on. But the real has additional advantage that you have this a priori bound about the interval maps. So that has a very, that helps a lot about the conclusions also. But the framework itself was set up with in a complex setting. But in real setting, you have additional information. Okay.
Thank you.
And
I think
in a full complex renormalization, including the satellite type, is, I think, still open.
Okay, Misha Lubitsch has a question, and we are going.
I would like just to make a quick comment, not a question, but quick comment, because Mitsu somehow formulated one application of the Shishikura theory and asked questions, are there any other applications? And actually there is the whole theory developed, so due to Shishikura a priori bounds, essentially a complete theory of neutral maps with combinatorial with rotation number of high type. So it is known under this assumption, so it is Shishikura and Fay-Young, that the boundary of the Ziegel disk is a Jordan curve. There is essentially full classification of the hedgehogs, etc., etc. So there are plenty of applications of this Shishikura theory which were somehow omitted. And so, but probably they will appear in some other talks of other of the other lectures of this mini course.
But my question about the totally different type of renormalizations, whether you can use this idea.
Okay, thank you. Let's thank the speaker again.
Thank you very much.